Hello everyone, is this thing on? Always wanted to do that. Hello everyone, thanks for tuning in. My name is Ignat and today we're going to talk about how to speed up disk encryption in Linux. Just so you know, this talk is pre-recorded, so you get the best quality, and probably because I have very bad broadband at home, but I supposed to be online when this talk is being streamed, so I should be here to answer all the questions you might have, but so the conference organizers promised to organize the online chat for us to communicate. However, if something goes wrong, if something doesn't happen as it should, every slide in my presentation, including the first one, has my Twitter handle, so please feel free to reach out with any questions you have during or after the presentation or anytime later. Okay, so let's go forward. First of all, a little bit about myself. I work at Cloudflare. I mostly do performance and security. I also am passionate about cryptography, and I enjoy low-level programming, something like Linux low-level, kernel implementations, bootloaders, firmware, and etc., and sometimes embedded systems. That's why we're going to talk a lot about Linux kernel these days. Okay, let's move to encrypting data. With disk encryption, we were going to talk about encrypting data at rest. So, what does it mean to encrypt data at rest? Data at rest means all the data you store on some kind of a persistent storage should be encrypted, and this is a must-have for any modern SaaS company, and probably most users these days encrypt their laptops as well, just to make sure. This is an easy way to make yourself and your data secure, and it makes much harder for a potential attacker to implement any breach in the system, because they get access to the data they shouldn't have. In terms of implementation, how is actually data being encrypted when it's stored? There are multiple levels of that, and to understand all of them, we need to review the storage stack further. This is a typical operating system storage stack. So at the top of the stack, we have our applications or services which run on our hardware or somewhere in the cloud. Application usually read and write data in files, so they communicate with the file system. File system translate these files into blocks, because the underlying storage is usually some kind of a block storage, and block storage can only read and store and retrieve data in blocks. So that's why underneath the file system we usually have an operating system block subsystem, which receive these blocks from the file system and then forwards them to some storage hardware. So block system just usually implements device drivers to access different types of storage hardware, like SSDs, spinning disks, NVMe disks, and other types of storage. So with respect to the storage stack, we can encrypt data at each level. We can encrypt data at storage hardware level. We can also, so technically you can just buy disks which do encryption for you. We can also encrypt data in the operating system block subsystem, which is the most typical use case. So example of that is in Linux we have LUKS dm-crypt, which we're going to extensively talk about in this presentation. In Windows we have the famous BitLocker, and you might have used FileVault on Mac OS. We can encrypt data in file system. There are file systems which actually support transparent data encryption. Specifically, Linux examples are encrypt-fs or the new fscrypt, previously known as ext4 encryption, but now it supports more file systems than just ext4. And of course, you can just encrypt the data in your application. You can use some kind of crypto library to encrypt your data before even sending off to the file system. Let's review pros and cons of each layer. So for storage hardware encryption, the obvious advantages are it's just there. If you buy a disk which can encrypt data, you don't have to do anything else. It will do it on your behalf. That's why you don't need much configuration. All you need to provide is like an encryption key or a password, and the disk will do it for you. It's fully transparent to your application and services, so they don't even know that the data they send to disk is being transparently encrypted, and it's usually faster than other layers because the encryption is done in the hardware and we don't use the host CPU resources to perform the encryption. The cons are there is no visibility into implementation, and most of the implementations are proprietary, thus poorly audited, which sometimes leads to poor security. And there was a recent study of security of hardware disk encryption on different disks, and the results were so bad. So Microsoft, for example, decided to switch to software disk encryption by default in its BitLocker implementation. Higher in the stack, we have block layer encryption. Again, it's very similar to hardware full disk encryption, except that it's implemented in the block layer subsystem of the operating system. It has similar pros, so it also requires a little configuration. It's also fully transparent for your application. Unlike hardware disk encryption, it's usually open and auditable. So if you use an open source system like operating system like Linux, you can look into the source and make sure it does what it describes to do. The downsides are it requires somewhat specialized crypto. So encrypting independent blocks on a storage is kind of a little bit of a hard problem. So you need to use a specialized cipher modes to actually do secure encryption. There are some performance issues which we're going to talk about in this presentation, because you use the host CPU resource to actually do the encryption, and your encryption keys stay in RAM because the host CPU needs to accept the encryption key to actually perform the encryption. Higher in the stack, we have file system level encryption. It's also somewhat transparent to applications. It's also open if you use an open source operating system. It is more fine-grained, so unlike block level data encryption, with file encryption you can have more flexibility in terms of you can encrypt specific directories, not the whole file system. You can have different keys per different directory, per user, etc., etc. And there is usually more choice of crypto, and there is some integrity support sometimes. The downsides are, again, performance issues. You do encryption in software, and encryption keys in RAM. It's more flexibility comes with the need of more complex configuration. You actually need to configure everything, which directory to encrypt, which key to use, etc., etc. And somewhat decreased security, because with file system layer encryption you have some unencrypted metadata. For example, with block level encryption, everything on the disk is being encrypted, including free space. With file system layer encryption, we only encrypt data in files, and sometimes the file names, but not the file size. We don't encrypt free space, so there is a lot of auxiliary information available to a potential attacker, which may or may not be usable depending on the threat. And on the top of the stack, we can do our encryption in the application itself. Again, it's open because we wrote it. It's very fine-grained, so you can write it as you like. And you have full crypto flexibility. You can use any algorithms you want, any way you want. The downside, again, your encryption keys are in RAM. You actually need to code it yourself, so it's not transparent to your application. You need to implement the encryption code, either using some library or writing from scratch, I don't know. You have the unencrypted metadata problem, and the downside is full crypto flexibility. Actually implementing crypto yourself is quite hard, even if you use a well-known cryptographic library, because there are a lot of caveats. So usually the good choice here is don't roll your own crypto and rely on some other method. So let's talk about block layer software encryption, and let's talk about Linux. Cloudflare, like many SaaS companies, we chose to use block level encryption in software because we don't trust hardware enough, the same as Microsoft, to do it for us, but we don't need all the additional flexibility and complexity from the application and file system side. We just want to encrypt everything. We don't want to pick the data which should be encrypted and which should not. We just want to say that we treat, with respect to security, we treat all the data equally, so we would like everything to be encrypted by default. And we use Linux everywhere. So that's why for the rest of the presentation we're going to talk about the implementation of disk encryption, block level disk encryption in Linux, which is known as LUKS or dm-crypt. So dm-crypt is a kernel side part of the disk encryption implementation. LUKS is the user space component. Okay, to understand what is dm-crypt or LUKS, we need to understand what is device mapper. So dm-crypt is a module which is part of a more generic Linux kernel framework called device mapper. And what that framework does, it allows modules which are part of this framework to be inserted between applications and the block device drivers to provide different additional functionality. Let's see an example. So let's say we have our application and services which read or write files from the file system, so they communicate with the file systems. And by default, the file system just communicates with block device drivers. They convert file I/O to block I/O and just send the blocks to block device drivers to be stored on real hardware. So device mapper allows modules to be inserted in between file systems and block device drivers, and depending on which module it is or in the implementation, we can provide additional functionality. So for example, there is a dm-raid module which is useful for implementing software RAID arrays. There is a dm-mirror module which can transparently back up your data to a secondary storage as you write it. And we're going to talk about the encrypt module, which transparently encrypts or decrypts block I/O requests as they go through to the device drivers. So let's zoom into the encrypt and let's see how it works on a 1000 feet view. So again, we'll skip the application part here. We have the file systems which send block I/O requests to block device drivers. So the encrypt itself inserts itself in between, and it basically encrypts every write before sending it to the block device driver and decrypts every read before passing it back to the file system. The nice thing about dm-crypt, it doesn't implement crypto on its own, but it uses well-defined Linux crypto API, which is also part of the Linux framework and provides generic cryptographic services. So we kind of have a separation here, like crypto implementation from its actual usage. But not everything is great. So at some point we noticed we have some performance issues with encrypted disk, and we decided to take a closer look how performant the Linux disk encryption implementation is. So we will do some dm-crypt benchmarking here. When you do any kind of benchmarking, basically you always introduce the bias of underlying hardware. So if you benchmark on a slow disk, you get bad results. If you benchmark on a fast modern SSD, you get better results. But to eliminate all the bias, let's do the benchmarking on the fastest storage layer possible, which is RAM. And in Linux, there is a module which allows you to to simulate a disk fully in RAM. So that's how we will try to remove the bias of the real hardware from our benchmarks. So to benchmark the purely dm-crypt implementation, we will create this 4 gig RAM disks. And by the way, all these commands have been pasted from a legal terminal, so consider it like a non-failing demo, and you can actually retrace the steps yourself on the dev laptops. So okay, we create this the first command, we will just create this RAM disk for 4 gig size. Secondly, we will allocate a file, a 2 megabyte file. I will just mention why right now. We will use that file to set up a dm-crypt instance on top of our RAM disk, but we will use it as a detached header. I will explain why in a second. So this sets up a dm-crypt instance on top of our newly created RAM disk. And finally, we just unlock that newly created RAM disk, so we get a new dm-crypt instance on top of our RAM disk. So here is our storage stack. So at the bottom we have our RAM-based disk. On top of it, we created a dm-crypt instance, so we can transparently encrypt data which goes into our RAM disk. For the purposes of this benchmarking, we also don't want to introduce any bias introduced by any particular file system implementation, so we will not use any file system here, but instead we will just write data directly to our dm-crypt instance, and we will compare to performance of the same data being written to the purely to the underlying block device in unencrypted manner. That's why we created a detached header here. So if we use the default non-detached header in LUKS, the header would be stored in the first 2 megabyte of our RAM disk, and if we just start writing random data bypassing our dm-crypt instance, we might accidentally override our header file and thus corrupt the whole process. So the detached header just makes it easy to both read and write from an encrypted instance and from the underlying device safely at any sector. Okay, so let's test the performance of the actual RAM disks unencrypted. So for this, we will create a simulated I/O workload, which is a simple 50-50 sequential read-write workload with a block size of 4 kilobytes. So notice we're using the DevRAM device directly here. So at this point, all the data being read and written is not being encrypted or decrypted. If we run this workload for a while, we will see that the average throughput we can get is, well, around 1 gigabyte per second of reads and 1 gigabyte per second of writes. So cumulatively we get somewhere around 2 gigabyte per second of read-write throughput, which is quite fast, and the read and write throughput is same here because we use a RAM disk, and it's not much different in terms of throughput either to read or write from RAM. So the next step, let's replay the same workload, but this time we will replay it on the dm-crypt instance on top of our RAM disk. So that means that every block will be encrypted or decrypted in transit on the fly. And if we run this workload, we will see that our throughput dropped up to 150 megabyte per second roughly in every direction, which is actually, we could expect that the throughput would be lower because now we use more resources, we use CPU to encrypt and decrypt data on the fly, but this kind of feels like 7 times slower is too much just for a simple encryption operation. Moreover, if we let's assume that our crypto is slow, but we can benchmark it. So the LUKS user space utility, which is called crypt setup, has a embedded benchmark which you can run, and you can compare the performance of different crypto algorithms. At this point, we know we use IS-XTS for encryption, and if you run that benchmark, you will see that purely encrypting and decrypting data, you can get somewhere around 2 gigabyte per second of throughput. So if we do simple back of the envelope calculation, we just assume the worst case that we reading all the data from disk in one step and sequentially just decrypting it in another step, we should get somewhere around 700 megabyte per second of throughput, but in the end we actually get slightly less than 300 megabyte per second of combined throughput, which is far less than even the projected worst case. So we tried to improve something. So we tried switching to different cryptographic algorithms, but according to Cryptsetup benchmark, ASXTS seems to be the fastest algorithm, at least on x86 platform. We also tried to experiment with different dm-crypt optional flags. So when you instantiate a dm-crypt instance, there are some additional flags you can specify with cryptic names say encrypt CPU and submit to encrypt CPU. They're marked as performance related flags. We tried these, but some flag actually even reduced our throughput, some flag slightly improved it, but with no significant improvement actually. At some point we were so desperate that our encryption is so slow, we tried file system level encryption, but in the end it ended up being much slower for our workload, and it would be potentially less secure because we don't encrypt the file metadata anymore. So we were at despair at this point. We hated the bad performance, but there was nothing we can do about it. We were so desperate, so we decided to ask the community, and at some point we wrote to the dm-crypt mailing list with our findings and say, hey, this performance does not look great, can we do something about it? But we received somewhat unuseful response. Is basically, if the numbers disturb you, then this is from lack of understanding on your side. You are probably unaware that encryption is a heavyweight operation. And at this point I was surprised, like, is crypto is that expensive? And what I did it just a simple scientific research by googling into Google search, is crypto expensive? And one of the first meaningful results I found is a blog post from our own company where one of my colleagues actually investigated the cost of crypto, but in terms of TLS. So Cloudflare does a lot of TLS connections, so at some point one of our engineers decided to take a look how much of a CPU we actually spend on doing crypto. And their conclusion was, actually we don't spend much resources, and on modern hardware crypto is very cheap, even at Cloudflare scale. So even if we perform millions of TLS connections a second, we don't spend too much CPU on cryptography because it's so optimized and implemented in hardware these days, then it's a minor thing. So if crypto is so cheap in terms of network connections, why should it be expensive when you store data on disks? There is not much big difference actually, and actually most TLS and data storage encryption use mostly the same algorithms. So at this point, because Linux is a nice open source operating system, we decided to look at the dm-crypt implementation and see if something can be improved. What we expect is a simple module which just encrypts or decrypts data as it passes through, but in the end it actually ended up being much more complex than we expected. So let's review the life of an encrypted bio request. So again, we have our file systems, we have block device drivers, and we have dm-crypt with crypto API in between. So when a file system issues a write request, dm-crypt does not immediately submit it to a block device driver. Instead, it queues it to be executed on an asynchronous thread. It runs one thread per dm-crypt instance at some point later. When that thread is actually being scheduled on the CPU and executed, that request is being sent to be encrypted to the crypto API. But modern crypto API is actually also asynchronous, so it might not process the request immediately, but decide to queue it again on a different asynchronous thread, which sometimes they call kcryptd, and they have like one thread per CPU, so it's slightly faster. So at some point, crypto API processes the requests, so it encrypts the write request and returns back and returns back to dm-crypt. But again, dm-crypt does not immediately submit the encrypted bio request to block device driver. It queues it on another structure, a red-black tree, for sorting. So it buffers some of the requests and sorts them to send the accumulated request in a sequential manner to a block device driver. When the requests are ready to be sent, they're not being sent immediately. They're a queue for sending on another asynchronous thread called dm-crypt write for sending when the thread will be executed by the CPU, and at some point later that request is being delivered to the block device driver. Similar thing happens for read. When a file system issues a read request, it's being queued by dm-crypt on another asynchronous thread called kcryptd.io. When the thread executes, so that request is being forwarded to the block device driver. So the block device driver goes to the hardware, retrieves the encrypted data, and returns it back to the dm-crypt instance. But dm-crypt instance schedules it for decryption, meaning queues it on a familiar already kcryptd asynchronous thread, which later sends it to crypto API to potentially another asynchronous thread called kcryptd, which actually performs the decryption, and then it returns the decrypted result to the file system. Well, that's a lot of queuing for simply handling one request, like read or write request. And this whole queuing reminded me of a nice presentation I saw on one of the SRECon, Usenix SRECon in Singapore from Google. This presentation was more generic, and it was about the dependency of tail latency with respect to queues in complex system. And it's a very interesting presentation on its own, and I strongly advise everyone to watch it. It's quite short, it's 20 minutes, but it's very compact and precise. But one of the takeaways I took out from there is that a significant amount of tail latency is due to queuing effects. And this kind of is the case here. So basically, we queue request at most 4 times for every write, and we queue each read request at most 3 times every read. And this can be quite damaging potentially on a busy system where system CPU is busy implementing, actually running our application logic. So before trying to modify anything, we would like to understand why these queues exist. So I don't expect someone to just randomly add like queues because they wanted to. There probably was a reason for these queues to be added there. So we decided to do a little bit of JIT archaeology. Luckily, Linux source code is stored in JIT, so you can kind of trace back the history and try to understand all the decision-making process around each code change. However, the initial kcryptd queue in dm-crypt was there from the beginning, from when basically Linux started to host its Git repository in publicly accessible repo. It happened in 2005, and it was there only for reads, with the comment, it would be very unwise to do decryption in interrupt context. And it kind of makes sense in 2005 because when you do a read request, some device drivers will just send your request to the actual hardware, and hardware may notify the host CPU that your data is ready via interrupt. So you may be actually processing read request in an interrupt context. However, so that's why kcryptd was added, not to do decryption in interrupt context. However, it was really necessary in 2005 because Linux Crypto API in 2005 was not asynchronous as it is now. So that's why dm-crypt had this workaround to perform decryption in interrupt context. These days, probably because Linux Crypto API is asynchronous itself, you don't need the kcryptd anymore, because Linux Crypto API should be smart enough to actually offload your encryption request to a synchronous thread and not do it in interrupt context in the first place. Later, some queuing was added to reduce kernel stack usage in 2006. So actually, my initial thought was the queuing was added for some, I don't know, some parallel processing of the request, but it's not actually the case. So kernel developers try to reduce kernel stack usage, so minimize the function call stack, and that's why they added this asynchronous behavior to actually like return from the function earlier and not make the stack deeper. However, kernel stack was increased later, so it might not be necessary anymore. Offloading writes to asynchronous thread and I/O sorting was implemented in 2015 with the following Git commit message. It's basically to improve performance on spinning disk, because spinning disks like sequential reads and writes more than random reads and writes, but it may improve SSDs, which might be the case in 2015 because SSDs were much less mature than today. The commit message also mentions that it's better for CFQ scheduler, which is actually being deprecated and removed from the modern Linux kernel. And immediately at the same year, there were commits to optionally revert some of the queuing. So we were not the first one to experience the performance degradation from the extensive queuing in dm-crypt. So these optional flags we tried earlier were actually added in 2015 to bypass some of the queuing, mentioning that in some cases it reduced performance. So things to reconsider. Most code was added with spinning disks in mind, where disk I/O latency is much higher than scheduling latency. For modern SSDs and modern other like storage, scheduling latency, CPU scheduling latency is comparable to disk I/O latency. So that's why this asynchronous behavior is much worse these days for performance. Probably sorting I/O requests in the encrypt violates the Unix do one thing and do it well, single responsibility principle. So sorting I/O requests is a task for I/O scheduler, and like probably the encrypt should not take part in it. Like, it should do what it's designed to do, like encrypt and decrypt data. And kcryptd may be redundant these days, as modern Linux crypto API is asynchronous itself, so there is no need for workarounds to avoid encryption in interrupt context. What it actually does is just offloads a buyer request to a synchronous thread just to be offloaded again in Linux crypto API. So we're just doubling the offload here. So having this in mind, we decided to do a cleanup. So we just decided to remove all this complexity and turn this complex module back into what it should be, a simple module which just encrypts and decrypts data on the fly. Also, to eliminate the potential impact of the randomized scheduling latency, we also wanted to try to use fully synchronous Linux crypto API and see how much performance gain can we make to do fully synchronous I/O request processing through the encrypt. So that's what we did. We did a simple patch to the encrypt module which introduces yet another runtime flag which we can flip now, and flipping this flag makes the encrypt to bypass all the queues and asynchronous threads in its implementation. Linux Crypto API is a bit more complicated because by default when you request a specific algorithm from Linux Crypto API, you might get different implementations. Like Linux Crypto API may have several implementations from the same algorithm, and it will pick the best one depending on the configured priority. But here we didn't want to take any chances. We want to use the fastest available ever ISNI x86 hardware IS implementation, and there are like synchronous variant of that. The problem is that the synchronous ISNI implementation in Linux kernel is marked as internal, which means it can only be used by other Crypto API modules and not outside modules from Crypto API. The another part here is that hardware implementation of IS and x86 system requires the usage of FPU, floating point unit. But sometimes you cannot use, in some rare cases, the floating point unit is not available for usage in some interrupt context, which again, if we do a fully synchronous processing, we may end up being an interrupt context when we do reads from the disk. So but it's very rare. So to address all these cases, we implemented yet another crypto API module called xtsproxy, which is a basically a dedicated synchronous IS XTS implementation. But it doesn't implement its own crypto on its own. It's basically a simple switch where this crypto API module, when it receives any encryption or decryption request, it just checks if we can use FPU in this execution context. If yes, which happens like 99% of the cases, we forward the request to the internal ISNI implementation, hardware-based ISNI implementation for our CPU. In rare cases where we cannot, and we can use this internal implementation because we are crypto API modules ourselves and we are allowed to call other internal modules. In rare cases where we can't use FPU, we just fall back to the generic, still synchronous IS implementation in software, which doesn't require FPU. It's much slower, but because we use it very rarely, we expect it shouldn't create too much of an impact. And the module itself is fully synchronous, so it will never offload any encryption request to any asynchronous thread. Okay, let's see our performance now. So we will restart our workload on our dm-crypt instance. We will start our workload first because we also wanted to show that our patch is flexible enough so you can flip flip the behavior at runtime even under production load with almost no impact. So basically we can experiment in production with this without bringing down and draining any servers. So that means we will start our workload first and then we will flip our behavior. So first step is to ensure our custom crypto module is loaded. So we just probe it. Then we execute this horrible command. What it basically does, it reconfigures our dm-crypt instance for two things. The first thing, we just tell the dm-crypt instance, instead of just requesting any IS-XTS implementation from the kernel and require on the kernel configured priorities to deliver the best one, explicitly request our xtsproxy module. So don't ask the kernel to make a decision for you, just request that particular implementation. And the second thing we do here is we just actually enable our runtime flag. So we tell dm-crypt now to bypass all the queues and asynchronous threads in the implementation for every request. The final step we need to do here is actually for our changes to take effect, we need to do this suspend resume thing. And here is the result. If you plot the read and write throughput on a fancy Grafana dashboard, you will see the following picture. So here is the place we enabled our flag, and we can see that our read throughput immediately more than doubled. The same thing happens for writes. So again, when we enable our custom patch, our custom code, our custom flag, we see doubling in the write throughput. To show you that we're not chasing ghosts here, this is a snapshot from actually our production system and real hardware. So this is a real SSD from our production, and here the yellow line is basically the measured IO latency of the raw disk itself, and the green line is the dm-crypt instance latency on top of the same disk. So here you can see, so basically before, by default, the dm-crypt doubles the perceived latency from the application's perspective, but when we enable our flag, these latencies converge, and we can actually see that the encrypted device software encrypted device latency is almost indistinguishable from like unencrypted device latency. So it's basically we are bottlenecked on the actual hardware latency here. Another interesting thing is like our service impact of our change. So here we did a three-way comparison of the service of the 99th percentile response time of a service which is responsible for fetching a cached asset from our CDN to a customer. And here you can see that the green line is the server which has an encrypted disk. The red line, which you see the significant impact introduced by applying Linux standard disk encryption on top. So like our service 99th percentile is much worse. And the blue line here is the same encrypted server but with our patched implementation. And you can see that from service perspective it's almost indistinguishable from an unencrypted disk. So again, we are not bottlenecked anymore on the encryption itself, we're bottlenecked on the performance of the hardware itself. So that's basically it. What we learned here, that Cloudflare introduced a simple patch which may improve Linux disk encryption performance around by 200 and sometimes 300%. Moreover, it's fully compatible with stock Linux dm-crypt, so we didn't introduce any new fancy crypto, any new fancy formats. We just like changed the implementation of the dm-crypt itself, and we immediately get the performance gain. And moreover, it can be enabled, disabled in runtime without service disruption, so we can actually have a like safe switch. If something goes really wrong, we can quickly disable it without affecting any of our services. We reconvince ourselves that modern crypto is fast and cheap. Don't rush to blame your performance issues on crypto. Try to look, usually the performance backend somewhere else, you just have to find it. And finally, extra queuing may be harmful on modern low latency storage. These patches were not submitted to the upstream Linux yet because they require a little bit of more work. So from our studies now, the patch improves performance and small block size, high IOPS workload, which is what our CDN cache workload looks like. But if you increase the read-write block sizes, like the tipping point is around 2 MB, it actually sometimes shows worse performance on some other workloads. Again, the whole setup assumes hardware accelerated crypto, so it's now currently works only on x86 platforms with hardware accelerated IS implementation present, which is more than x86 platforms, but still. And finally, your mileage may vary. We tested it on our workload, it improved our workload, but maybe on different workloads it may behave differently. So always measure before deploying it to production, and we will be grateful if you let us know the results so we can improve, together we can improve the implementation further and submit it to the upstream Linux kernel project. So some links. First two are just the man pages for the crypt setup, user space utility, and dm-crypt in general, or device mapper. You have to see those if you don't know how to set up Linux disk encryption. The third link is our blog post about the contents presented in this presentation and much more, and there are also more details and numbers, so I advise to go there for further details. And finally, our GitHub Linux repository, where the patches discussed in these presentations are published, so you can try them yourselves, and please leave us some feedback. That's basically it. Now it's time for questions. I hope I'm online now on the chat waiting for your questions. If not, please reach out on Twitter. I would be happy to follow up on any questions you might have. Thank you, stay safe, and have a nice day.